Look back at the earliest days of computing, and you'll find a system built on absolute physical certainty. Every calculation, every string of data relied on binary logic. It is an uncompromising universe entirely defined by ones and zeros. This language is derived from its simplest physical form, the punch card. A specific location on the paper either has a hole or it doesn't. Yes or no, true or false. Decades of digital architecture and the software we use every day function precisely because they rely on that definitive binary baseline. Curious, shifting tone. But as we move into the realm of quantum mechanics, that certainty disappears. The rules change. Instead of the rigid toggle of a classical bit, quantum computers use a qubit. This unit exists in a state of superposition, acting like a blurred, vibrating sphere of multiple probabilities at once. The operational difficulty is that a qubit behaves as a 1, a 0, or a blend of both simultaneously, right up until the moment it is measured. This creates a physical recording problem. Our existing hardware demands definitive answers. We need a way to track a system that refuses to pick a single state. These handwritten notes outline a conceptual bridge, a framework labeled Qxbin. The author proposes using what they call a reverse binary probability matrix to solve the recording roadblock. To manage this, they construct a custom mathematical notation. Instead of fixing a variable to a static number, the formula expresses a fluid probability. By assigning distinct multi-state variables to the numerator and denominator, the math captures the probability of different states existing simultaneously. This notation formats these abstract probabilities into a structure that classical, binary logic can recognize and process. Methodical, this logic changes the physical shape of recorded data. The traditional binary chain is mapped out here as a straightforward, linear row. The quantum chain beneath it discards that straight line. It uses cross-shaped spatial clusters to represent different nodes of probability. The notes suggest testing this spatial theory with a physical experiment, a grid-based punch card system. The system would use magnetized paper and the Hall effect to record data. This allows the hardware to detect subtle magnetic variations that represent different potential states. To simulate a qubit superposition, the process uses a coin toss. The randomness of the flip provides the multi-state input that the magnetized paper records. This is a macroscopic engineering blueprint. It takes abstract math and outlines a tangible experiment to model quantum behavior on a workbench. Building curiosity. The intended application for this setup is listed at the bottom of the notes, a personal qubit simulation processing system. Standard quantum computers require sub-zero temperatures and massive lab infrastructure. By using magnets and the randomness of a coin toss, this prototype attempts to model that same behavior at room temperature using simple physical parts. This approach shifts the focus away from expensive laboratory processors. Instead, it tries to create a desktop simulator that puts quantum logic into the hands of an individual. Signed in 2026, the author leaves us with an analogy for this technological transition, building an airplane to replace a horse. We understand the classical world. We know how a horse gallops across a plain. Its speed and its limits are familiar. But the quantum future operates in a different dimension. Trying to grasp its mechanics with our current logic is like trying to explain taking flight to someone who has only ever known a saddle. The success of this specific magnetized paper prototype is less significant than the attempt to model these complex interactions using basic physical materials. The Qxbin stands as a record of a classical engineer trying to map the territory of the quantum future using the tools of the present.